Hey everyone, it's Dr. D-Flo, and in this two-part video series, I'll show you how to create 3D printer filament from fresh plastic pellets, and then in a subsequent video, how to recycle failed or unwanted 3D prints back into filament. This first video will be focused on extruding and spooling filament from new pellets, starting with a general overview of the process. I will then take a deeper dive into the technology and materials behind plastic extrusion. Of course, I will have to answer the most important question: how much money do you save by making your own filament? And finally, I will end this video by extruding quite a few different materials, including reinforced composites. And with that, let's get started.
Dr. D-Flo.
All this equipment was provided by Filabot as part of their plastic recycling lineup. I'm not going to review the equipment because frankly, at this price point, there's nothing to compare it to. This is the most industrial equipment that you can purchase that can still be powered off a residential 15 amp outlet. What I am going to assess is the ease at which filament can be produced by a hobbyist or small business. Over the past year, I've produced several hundred kilograms of filament for my classes and makerspace at my university, with many spools having recycled material in them. So let's get into the process. This long machine is the workhorse behind the filament production process and is known as the X6 extruder. It takes plastic pellets and melts them before forcing them through the nozzle or die. The melt takes the shape of the die, which in this case is a 1.75 millimeter diameter hole to match our desired filament diameter. To get the pellets from the hopper to the nozzle, a screw such as this one advances the pellets forward by rotating. In doing so, the pellets grind against each other, generating heat through friction. Extruders with larger screws allow more material to be conveyed and melted. And this is one of the reasons why filament extrusion at home has not really taken off, because the smaller and cheaper extruders cannot melt plastic quick enough to make this process worth your time. The low-cost fill extruder that I teased in my How to Build a 3D Printer video took over 8 hours to make enough filament for a 1 kilogram spool. This will be discussed further when we get to the economics of this process, but for now, let's go ahead and fire this thing up. The extruder has reached its set temperature. I went ahead and clicked start, and now you can see the plastic is pooling up down here. If you look closely, you can see the plastic melt has a slightly larger diameter than the orifice of the die. This is known as extrudate swell and is due to the elasticity of the molten plastic. This increase in diameter would not be compatible with 3D printers expecting a 1.75 millimeter filament. What we can do to combat this is pull on the melt to stretch it out axially to keep it from swelling radially. If you're not following, I will revisit this point in a second, but first, to be able to pull on the plastic, it must be cool enough so that it can be gripped without deforming. The molten plastic can be air or water cooled. Filabot sells both an air path, which uses fans to cool the newly extruded filament, and a water bath, which of course uses water. For fast extrusion speeds, the high cooling capacity of the water bath will be necessary. The air path, which I have, is easier to set up and requires less maintenance, but it is a little bit loud. I have 2 air paths for increased cooling. I'm going to pull the molten material across these 2 air paths. I have to match the speed at which the filament is being extruded. Too quick and the filament may thin out and break, while moving too slow will cause material to clump together near the die. By the end of the cooling stage, the filament should be hard enough that it can't be easily deformed. We've now reached the spooler, which has an indicator on the entrance. This measuring device will monitor the diameter of the filament. Directly on the other side are the drive wheels, which will grab and pull the filament. Again, the filament must be solid at this phase, or else the desired circular profile of our extruded material will look more like a pancake after the drive wheels smush it. With the drive wheels now guiding the filament, we can check the indicator for a diameter measurement. It looks like we're at about 1.86 millimeters. If we pop up to this monitor, we can see the filament diameter being tracked over time. This top number is the current diameter, and below it are the highest and lowest values that the diameter has been measured at. The highest being 1.92 and the lowest 1.75. So we are too high for that 1.75 millimeter target diameter. This larger diameter filament is likely because of extrudate swell. As mentioned previously, we can stretch the material coming out of the nozzle along its length to decrease its diameter, which can be accomplished by increasing the speed of the drive wheels. All of the controls on the spooler are analog, so you can adjust the drive speed here. and then you can check the indicator. And you keep doing this until you get 1.75 millimeters plus minus 0.05 millimeters, or about 50 microns, which is the industry standard. I'm increasing the drive wheel speed. It's pulling more on the filament. We need a quicker speed as we're still at 1.86 millimeters. It can take a little bit of time for an adjustment made on the spooler to show up on the indicator as the filament has to traverse all the way across the air paths. Now we're getting close to 1.8 millimeters. Increase that speed a little bit more. This fine adjustment only occurs when you feed the filament through the drive gears, and it will largely remain constant throughout the spooling session. Next, I'm going to load a standard 1 kilogram spool. What you will notice is that the spool spins at the same RPM as the drive wheels. However, to make sure that the filament spools with the right tension, ideally just tight enough to make sure the filament is touching the previous row, the spool will have to spin faster when it's empty and slower when it's almost full due to the growing circumference of the spooled material. Filabot uses a tension clutch mechanism where once there's a certain amount of resistance, the spool will stop spinning. The amount of tension can be changed by adjusting this nut. This is a pretty simple mechanism which works well enough that I've never had a tangled spool, but you're not going to get perfect layering of the filament. Before we start spooling, we need to pass the filament coming off the drive wheels through this traverse mechanism. This ensures that the material is laid across the whole spool. When it reaches one of these two grommets, if I turn it on, it'll hit this grommet, it'll push this post, and then it'll switch directions. This allows the filament to cover the full spool, and adjusting these grommets allow for spools with different widths or sidewall thicknesses to be used on this spooler. What I'm going to do is cut it, pass it through the traverse mechanism, let it come around back, stick it in the hole so that it can't unspool. The indicator and my computer are of course tracking the diameter of the filament, so I can be confident that the whole spool is within spec when I get back. The last thing is that all this extra material here, I'm not going to throw it away. I'm going to recycle it by pelletizing it and throwing it back into the extruder. Definitely subscribe for the next video to see that part in process. It'll take 35 to 40 minutes to spool at this rate, but before I walk away, I need to top off the plastic pellets. A majority of the material going into the hopper is the base resin, in this case PLA. The colored specks are the concentrate that give the filament its green color. If you've seen my large format 3D printer series, which also uses a screw extruder, then you may have noticed that the extruded material is not always a uniform color. This is because the print head uses a very small screw, which is not long enough to sufficiently mix the colorant with the base material. This is not the case with the X6, where I always expect a uniform color because it's got a very long screw. So we're just over 40 minutes and we have a very full spool. Of course, when I'm recording, it decides to spike at the very last minute and just pushes us over the tolerance of 1.81. But that's okay. This spool is going to print totally fine. What I want to do now is swap that spool. We'll adjust the drive speed because you can see here that the average filament diameter was a little bit above that nominal green line, which is 1.75. So back to what I was saying, I'm going to swap the spool, increase that dry speed just a little bit so we don't see that spike again for the next one. I'm just going to wait for the traverse to get to the end, so we start on one side of the spool and it spools evenly across it. And that's it. I can restart the capture and we'll be good to go. I want to quickly show that the last spool was an exception to the norm. I'm working with a white colorant now, which was in spec the entire 330 meters that make up the spool. Also, I was able to shave off 10 minutes from that 40-minute spooling time, so this spool is about done at 31 minutes. This is about the max speed I can achieve with PLA, as I'm limited by cooling capacity at this rate. Next, let's talk about the components and fundamentals of plastic extrusion. At first glance, filament extrusion seems simple, but this process is complicated by the demands for perfection. If filament falls out of spec for even a second, the spool has to be thrown away, or else you risk jamming your 3D printer. Some plastics are more difficult to extrude than others and may require a different nozzle or even screw geometry to get consistent results. Right now I have the X6 configured in a general purpose setup that allows for the extrusion of most plastics at an average speed. To go through this setup, let's first take a look at the die. This is a standard length die with an integrated mesh filter. The mesh keeps contaminants from making it into the filament, which could plug a 3D printer's nozzle. In addition to keeping small particulates out of the final product, the mesh also creates a back pressure which mixes the colorant and base material together for a nice even color. However, this back pressure does limit output, but I would never recommend foregoing the filter even with this drawback. The only time I don't use the mesh is when working with composite materials such as carbon fiber and glass-filled plastics, because of course the mesh will filter out those reinforcements. The mesh is supported by a component known as the breaker plate, which is just a disc with some holes drilled into it. Interestingly, molten plastic can remember its last motion, which before the breaker plate, the plastic was rotating with this screw. A secondary role of the breaker plate is to eliminate this rotational memory by forcing the plastic to go through these holes that are actually aligned with the extruder. This way, the plastic melt exits straight out of the die and doesn't curl up. The actual length of this 1.75 millimeter hole that the plastic will conform to is quite short. Philibot sells extended length nozzles, which are required when running at higher extrusion speeds. Generally, longer dies further straighten out the flow, which reduces the swelling of the extrudate and improves the final shape of the filament. However, longer dies increase the pressure inside of the barrel, which requires more power from the motor to push the same amount of material through when compared to a standard size nozzle. This can also result in a higher melt temperature, which can degrade the material or require additional cooling upon exit from the die. The single most important mechanical element of a screw extruder is, of course, the screw. Some of the lower cost extruders, such as the Extruder, uses a drill bit for the screw. But as you will see in a second, the geometry of a proper extruder screw is more involved and optimized for melting plastics. As I'm pulling the screw, I want to emphasize that 80 to 90% of all energy that goes into melting the plastic pellets comes from the mechanical rotation of the screw. While there are heaters on the barrel, which we will discuss later, they only account for a small amount of the melting. This is very different than an extruder on an FFF 3D printer, where only the heaters are responsible for melting the plastic. The rotation of the screw causes the pellets to rub up against each other, the barrel, and the screw itself. This friction generates the heat that starts the melting. Once some of the plastic melts, the helical motion of the screw causes the thick molten plastic to deform. This deformation causes a second form of heating known as shear or viscous heating. The point here is not only is the screw effective at transforming mechanical energy to thermal energy, but the heat generation will be relatively uniform throughout the material. Uniform heating is critical when processing large volumes of plastics, or else degradation will occur. Okay, I got the screw in hand. This is a 16 millimeter diameter screw that is 384 millimeters long, yielding a 24 length to diameter or LD ratio. Screws with a higher LD ratio provide better melting and mixing. Lower cost machines use much smaller screws and consequently will have a lower throughput and less consistent output. In addition to its length, this screw also has a taper which forms 3 distinct regions based on how deep the flights are. The deepest flights are where the pellets are fed in, and this section is aptly named the feed section. On the opposite end, the flights are shallower. This is known as the metering section, which will be occupied by the melted material that will soon be pushed out of the die. The middle section is the transition or compression region, where the screw flights become shallower in a linear fashion. This compression is critical for the proper functioning of the extruder and is where the melting of the plastic pellets occurs. To understand the importance of compression, we can compare the volume the plastic pellets take up as is and after they are melted. Here's about 20 grams of plastic pellets. You can even see the free space between the pellets in this graduated cylinder. When I melt the pellets, the molten material packs much denser. Without compression on the screw, there will be free space or air present with the molten plastic in the screw flights. This trapped air will try and escape through the die, causing defects in the extruded filament. This is perhaps the easiest benefit of the compression region to explain. However, the amount of compression also plays an important role in the melting of the plastic, mixing of the colorant, and building up pressure required for consistent and controlled flow of the material through the die. Philibot sells 4 different screws with varying level of compression, from no compression to high compression. Here I have both the standard compression and high compression screws. The difference is subtle, but the channel depth in the metering section is even more shallow for for the high compression. The screw selected is based on the plastic that will be extruded. A high compression screw is more aggressive in its heat and pressure generation and used for plastics that have a high melt viscosity. Most of you are probably familiar with the concept of viscosity, where fluids with high viscosity are less likely to flow. Of course, honey has a high viscosity compared to water. Depending on their chemical structures, plastics have a wide range of viscosities when they are melted. Those with higher viscosities take more convincing to get them to move down the barrel, which is accomplished by a higher, more aggressive compression in the screw. Examples of plastics with high melt viscosities that benefit from compression are PET and nylon. But some plastics, especially amorphous ones such as ABS, HIPS, and polystyrene, have a lower melt viscosity and may be sensitive to thermal degradation. Thermal degradation occurs above the plastic's melting point and results in the breakdown of the internal structure of the material. For thermally sensitive materials, the degradation temperature is much closer to the melting point. So care has to be taken not to overheat the plastic melt. A low compression screw can prevent this overheating. Lower compression screws are also ideal for composite materials such as the carbon fiber and these carbon fiber reinforced ABS pellets. High compression can shear and break these fibers, which negates the structural benefit of this additive. Generally, high compression screws should not be used for composite materials. Now, I have oversimplified screw extrusion and have not even touched on the can of worms that is the shear thinning behavior that most plastics exhibit. But what I do want to emphasize is that the geometries of the screw matters, with the wrong selection resulting in a degraded filament or a jammed extruder. The ability to easily swap between screws is a major benefit of this design. The next thing I want to discuss is why this extruder is so expensive. At the time of recording, the X6 is about $15,000. I don't know all the economics behind building an instrument like this, but I can quickly show you some costly components. First is the screw and barrel assembly. You've already seen the screw, which is not easy to machine due to its small cross-sectional area and length. But there has to be a tight tolerance between the screw and the barrel such that the screw can turn freely while minimizing the amount of polymer that can leak backwards between the screw flights and the barrel. This clearance is usually only a couple thousandths of an inch or less than 100 microns for the whole length of the barrel. If the clearance is too large or the screw wears down over time, then performance of the extruder will suffer. The next expensive assembly can be seen if I remove the side panel of the extruder. I've taken the back cover off, and just for your reference, the output is now on this side. The whole thing's been flipped around. But now we can talk about the next expensive assembly, which is this 90-volt quarter horsepower DC motor with a 28-to-1 gearbox. It takes a tremendous amount of torque to turn the screw because so much of that mechanical energy is going into heating and advancing the plastic. That torque is needed at low RPM, so a DC motor is a must. With the cover off, we can also see the barrel. This is a great time to talk about the barrel heaters. There are 3 separate heating zones which correspond with the different regions of the screw: feed, compression, and metering. The purpose of the heating elements is to help with the initial melting of the pellets at the end of the feed section and to ensure a uniform temperature in the metering section right before the material exits the die. In some cases, the mechanical heating from the screw will be too much, causing the polymer to overheat. For this reason, there are fans for the 2 later sections, the metering and the compression, which can cool the barrel if needed. The plastic is most likely to experience overheating in the compression section because of the high forces at play. The X6 having these 3 separate heating zones is a huge benefit over other models with a single zone, as this overheating can be mitigated through allowing excess heat to conduct through the barrel. This can be facilitated by having a lower barrel temperature. However, a low barrel temperature near the nozzle could result in plugging or poor polymer flow out of the die. So it's critical that the metering section has its own independent temperature control. The fan speed is controlled by knobs on top of the X6, and the temperature of the 3 screw regions are controlled through PID controllers. There's a 4th PID controller for where the hopper meets the screw, right here. This is labeled as feed. We want a low temperature here to prevent the pellets from sticking to each other at the interface between the hopper and the screw. Bridging of pellets at this location would stop the flow of material. I always have the fan associated with this section running at max speed. Of course, temperature set points and fan speeds will be determined by the plastic that is being extruded. As I've emphasized, the barrel heaters only account for a small amount of melting. Consequently, cranking up the barrel temperature largely does not result in higher melting rates. In fact, this usually results in degradation of the material near the barrel surface. However, if the barrel is too cold, then there will be temperature gradients in the molten material which can cause the extruder to plug, or at the very least, induce inconsistent extrusion. The extrusion rate can be increased by upping the speed of the DC motor, which is accomplished by turning this knob. An analog voltmeter and ammeter gives us insight into how much power is required to turn the screw at the current speed. Multiplying the volts reading by the amps reading will give the power draw of the motor in watts. Faster speeds or higher screw compression will require more motor power. Again, most of this motor power is converted into thermal energy, so in a way, this is a measure of heat input into the system. Higher RPM will increase the average melt temperature of the polymer, which will require more cooling after extrusion, or may not have a high enough viscosity to maintain its shape when leaving the die. A longer die, as discussed previously, can combat this, which is known as extruder drool. Filament claims that the X6 is capable of 4.5 kilograms or 10 pounds per hour of output, but this is largely dependent on the setup of the machine, the plastic being processed, and the amount of cooling on the other side of the die. With my conservative general purpose setup and 2 air paths, I see closer to 2 kilograms per hour when extruding PLA. This is a good segue into the economics of extruding your own filament at home, at a makerspace, or even at a small business. I can tell you already that the X6 is not the appropriate machine if you want to go into producing filament for sale, but it can significantly cut down the cost of running a farm of FFF 3D printers. The savings come from plastic pellets costing significantly less than a spool of filament. Pellets are also cheaper when purchased in bulk. My 1250 kilogram PLA super sack from Filament is approximately $6 per kilogram. Of course, such a large quantity is difficult to take delivery of at your house. Trust me, I know. So Filament also sells smaller quantities which ship through residential carriers. 20 kilograms of pellets in this form is about $7.50 per kilogram. In addition to the pellets, you're probably also going to want to add colorant to make your filament more visually appealing. I add colorant at a ratio of 2 to 100. Therefore, a $200 container of colorant, which has 2.2 kilograms of concentrate, is good for around 110 spools. That's an additional $1.80 per spool. The only other cost is power consumed. Again, another major benefit of this system is that it can run off residential 110 or 220 volt. Everything here, the extruder, air pass, and spooler, will consume at most 1.5 kilowatt hours when running, which where I live is 15 cents per hour. And yes, I know my electricity is ridiculously cheap, but even if your power is an order of magnitude more expensive, this won't cut too deeply into the cost savings. So, assuming that I purchase PLA pellets by the super sack, add colorant, and produce 2 spools per hour, it'll cost about $8 per spool. Now we can calculate our return on investment, or ROI. While there may be cheaper commercial offerings, most reputable brands sell PLA spools for around $20. All the equipment here can be purchased together for about $18,000. And with $12 of cost savings per spool, I will need to make 1,500 spools before I break even. This would take 94 8-hour days of spooling. In reality, I can produce filament even cheaper because I use a percentage of recycled material in each of my spools, which lowers the material cost. We're going to discuss this more in the next video. Also, extruding exotic plastics and composites can further increase ROI. I can create carbon fiber reinforced ABS spools for $24 per kilogram, when commercially available filaments are twice this price. But there is one cost that we left out: labor. Because the filament changes are relatively spaced out and quick to perform, I'm able to run the extruder line when accomplishing other tasks. However, if you're running the system to produce filament that you are trying to sell, the production rate is too low and labor costs will destroy your margins. Industrial extruders that are designed to produce 3D printer filament can extrude 20 to 50 kilograms an hour. This is a much more efficient use of a technician's time. I just want to make sure that if you purchase this equipment that you have the correct expectations. The 1,500 spools required to break even is a lot of filament. For my classes in makerspace, we consume anywhere from 10 to 20 kilograms per week during the academic year. It'll actually take longer to consume the material than for me to produce it so that I can realize my ROI. In a research setting, the system has a lot of other benefits, such as being able to formulate custom filaments from either new plastics or mixing in additives to improve existing materials. It's also possible to combine different ratios of colorants for bespoke colors. However, it's still better to purchase a colorant of your desired color because single screw extruders are not the best at precise mixing of low percentage components. And that's the economic breakdown of this process. Up to this point, I've only worked with PLA, but if a plastic is sold in pellet form, then it can be extruded as a filament. However, just because you can make a filament doesn't mean that it will print well. HDPE and polypropylene are easy to extrude but terrible to 3D print because they both warp significantly. The reason that some plastics can be 3D printed and some cannot is because these materials exist with varying levels of internal structure known as crystallinity. Highly crystalline plastics are very organized on the molecular level, allowing the building blocks of the plastic to pack tightly and take up less space. When melted, this organization breaks up, causing the molten material to take up more volume. When the molten plastic is allowed to cool, this order reforms as the molecular chains repack, resulting in shrinkage. HDPE and polypropylene exhibit high crystallinity, so when these plastics go through the heating and cooling cycles that are inherent to 3D printing, they warp due to this shrinkage. Here I have a graduated cylinder full of melted HDPE. As it cools, you will see it shrink radially, away from the glass walls. It should be noted that the amount of crystallinity depends not only on the type of plastic, but also the cooling rate. A slower cooling rate will provide more time for the dense ordered structure to form. Once the HDPE slug has cooled, it has decreased in diameter enough to slide right out of the cylinder. On the other end of the spectrum, there are amorphous plastics that have no crystallinity. These include popular resins such as ABS, ASA, and HIPS. The low crystallinity of PLA and PETG often causes these plastics to be grouped with amorphous materials. Plastics with low or no crystallinity are more dimensionally stable when heated and cooled. All of these plastics can be printed on a hobbyist 3D printer when configured correctly. In addition to better printability, amorphous materials are also easier to extrude as a filament because they melt and flow more evenly. With that said, I want to extrude some ABS now. Before I can do that, I need to clean out the remaining PLA and colorant that is in the barrel. Anything in the extruder that is not ABS is a contaminant that can not only affect the quality of filament, but also the throughput of this machine. To start the cleaning process, I use a purge compound that forces out the previous material. This compound foams slightly, which helps it expand and clean all the different places contaminants could be hiding. What you may notice is how long it takes for the blue shade to dissipate. This illustrates how much holdup there is in this machine, and of course the importance of cleaning it. With a small extruder like this, it's always good practice to pull the screw and clean it with a brass wire brush between materials. A film of degraded plastic can build up on the screw surface, which needs to be removed. While a bit tedious, I've always seen the performance of the extruder directly correlate with how much time I put into cleaning between materials. Before inserting the screw, I also clean the barrel, but this time it's with a brass pipe cleaner. I have the ABS spooling now. As I mentioned, amorphous plastics generally flow better, and as a result, it's easier for me to set the dry speed to get that filament diameter centered around 1.75 millimeters. However, there are two careful considerations that need to be made when working with ABS. The first is that when the material melts, it off-gasses noxious fumes. I have an exhaust system that is aimed right at the die to capture those gases and get them out of this room. The second issue is that ABS is a hygroscopic material, meaning it readily absorbs water from the air. In some cases, up to 5% of the material's weight can be water. When this moisture gets into the barrel, it boils and its gas escapes through the die, causing voids in the filament. Rough filament is usually a telltale sign that the pellets went into the hopper wet. For this reason, I always dry ABS and all my other pellets for 5 hours at 80°C or hotter, depending on the material. While I'm on the topic of ABS, and with this spool almost finished, I'm going to switch to carbon fiber reinforced ABS. I had mentioned previously that amorphous polymers exhibit less shrinkage, but these materials can still warp as a result of internal stresses that occur when 3D printing. The chopped carbon fiber in each one of these pellets can combat this warpage and just provide a stronger overall material. A chopped carbon fiber composite won't be as strong as a continuous fiber, but nonetheless it is superior to neat ABS. The only change that I need to make to the machine is switching to a nozzle without a mesh filter. Also, it's not possible to color the carbon fiber because it's already black. Here I have one of my Vorons printing a motor mount out of the carbon fiber reinforced spool that you just saw. I used normal ABS settings but achieved less warping, stiffer parts, and a nice matte finish with this filament. You do have to be careful as the filament can be brittle, so a reverse Bowden tube and a straight path to the extruder is necessary. But with those benefits and a cost close to buying a PLA spool off of Amazon, it's very difficult for me to not print with this material all the time. Let's swap over to PETG, a plastic commonly used for food containers and drink bottles. The cool part about these specific PETG pellets is that they are created from recycling those previously mentioned items. But whether your PETG pellets are new or recycled, this material is one of the more difficult plastics to extrude due to its relatively high melt viscosity. As discussed previously, we will swap out the standard screw for a more aggressive high compression screw for this very reason. We also need a longer die because counterintuitively, PETG can drool when coming out of the die, which you can see now when a standard length die is used. This may defy your expectations because PETG should maintain its shape upon exit from the die because of its high melt viscosity. Well, viscosity decreases with temperature and the high forces associated with the screw can overheat the material. The longer nozzle gives the molten plastic more time to cool off and maintain its shape before exiting. The potential for the material to overheat also informs the temperatures of each of the heating zones. PETG's melting temperature is between 230 and 260 C, but all three temperatures are set below this range to allow excess heat to conduct away from the material and through the barrel. This is just more evidence that the barrel heaters really don't play that big of a role in the melting of the plastic. The screw, on the other hand, is generating a tremendous amount of heat. The amount of power the motor is putting in is literally off the scale. And even though the motor is having to work this hard, the filament output for PETG is much lower compared to our other plastics that we've extruded. I am lucky to get a spool every hour and 15 minutes. So to recap, PETG requires a special setup, has high power demands, and a low output. Are there any other issues? Well, similar to ABS, it's also very hygroscopic. You can see bubbles in this filament from pellets that were not dried completely. Proper drying is absolutely critical, not only for extruding PETG as a filament, but also when printing it. But once you get the settings tuned in, with a little more time on your hands, you can make some nice spools. Also, if you don't use any colorants, as I've elected to, you can create transparent filament given the correct extrusion temperatures. I had mentioned previously that PETG has low crystallinity. Generally, crystalline structures within a plastic object obstruct light due to their density. So if you can decrease or eliminate the formation of crystal structures when the material is cooling, then you can make it more transparent. The best way to do this is to cool the plastic quickly. This concept is, in many ways, analogous to quenching a metal. So extruding PETG at a high temperature and then cooling it quickly will create a transparent filament, but extruding it at a low temperature and cooling it slowly will result in a more opaque material. Properties like this are one of the reasons that plastics are just so fascinating to me, and being able to extrude all these different materials has taught me a lot about how to process them both on this extruder and the one on my large format 3D printer. I've created a document with my own settings and observations for extruding most printable plastics. Head over to drdflo.com or click the link in the description for that information. Clear PETG is an awesome filament for vase mode. If you can keep the walls thin enough, then your object will be translucent. Let me know in the comments below what your favorite filaments are to print. For the next material, I'm going to extrude HIPS, or high impact polystyrene. When most people hear dissolvable support material, they think of polyvinyl alcohol or PVA. However, HIPS is also a suitable support material as it is soluble in a citrus fruit extract known as limonene. HIPS pairs well as a support material for ABS and nylon due to its similar melting temperatures and printing properties. However, it can also be used as a support material for other filaments, and I suspect that it'll become more popular as the price of PVA continues to rise. I also use HIPS as a normal filament because it has great impact resistance, mechanical strength, and is as cheap as PLA for me to extrude. However, HIPS is thermally sensitive and can degrade if it experiences too high of temperatures or is heated above its melting point for a prolonged time. Given this, when I first tried to extrude HIPS, I opted for a low compression screw to minimize viscous heating. However, I was never able to get a consistent filament diameter, as you can see here. These steep, random drops indicate that there is a feeding issue, almost as if there are gaps in the flow of material causing the filament diameter to decrease rapidly. Now, there are other issues that could cause this, but it's likely that I need a higher compression screw. I switched to one with a standard compression and no longer saw this problem. Of course, I could have skipped this troubleshooting, but I wanted to give an example of how I used the filament diameter measurements to change the configuration of the extruder. I have several more examples on that previously mentioned document, which you can check out. At this point in the video, I think you have a good feel for extruding plastic pellets as a printable filament. When we start to introduce ground up recycled material, this process gets a little bit more difficult. We're going to tackle that in the next video. If you enjoyed part 1, be sure to hit the like button. If you want to support the Dr. D-Flo channel and this educational content, hit the join button, become a channel member. And with that, I'll catch you in the next one.